Hi everybody, my name is Taylor Richardson and I will be discussing my answers for the written exam for Module 3 today. So we'll start with the first question, and this question was about the divisibility test for the different numbers to know if they can evenly be divided into the larger numbers that we see. And this can easily be figured out using the simple divisibility test that we have learned in this chapter. And I have a little chart made out using some of the numbers. For example, we know the number 2. If it's divisible by something, it's divisible by a number that's going to be even. And if a number's even, we know that the number in the ones place is either a 0, 2, 4, 6, or 8. And that's a pretty easy one. We know just simply that if a number is even, that it's going to be divisible evenly by 2. There's not going to be any crazy numbers or anything. And so we'll move on to the number 4. If a number is divisible by 4, we can easily find out if it's a large number, if it's divisible by 4, by adding up the last 2 digits of the number. So for example, a number like 1,234, we would add up the 3 and the 4 and test to see if the number 7 is divisible by 2, or by 4 rather. And if so, then the whole number is divisible by 4. So we know that 7 is not divisible by 4, so the number 1,234 would not be divisible by 4. And it goes on with numbers 5, 6, and 10 there. They're pretty simple. And then we had a question, rather, to find out if a number is divisible by 3. And we can find out if a number is divisible by 3 by finding the sum of all of the digits in the number. So for example, the number 197 listed here, we can know that if we add up the 1 plus 9 plus 7 and equals 17, and we need to find out if 17 is divisible by 3. And if it is divisible by 3, then the whole number, 197, is divisible by 3. But if it is not, then we know that 197 is not divisible by 3. And so we know that 17 divided by 3 is roughly 5.6 or so. So the number 197 cannot evenly be divided by 3. And this also works for the number 9, the same method. You can add up the digits in a number and see if that number, the sum, is divisible by 9. And if it is, then the whole number is divisible by 9. And we can see an example there. And then we moved on to see if a number was divisible by 7. And so this one was a little more confusing. We had a formula to use. And the formula is m equals q minus 2r. And we know that if the m in the equation is divisible by 7, then the whole number n is divisible by 7. For example, 2,951, is that divisible by 7? We know that it's only divisible by 7 if 295, the first 3 digits, minus 2, which is the 2r, 1 would be r, and then we would multiply it by 2 in the equation. And so we know that equals 293. And then we can take 293 and see if it's divisible by 7 by taking 29, the first 2 numbers, which would be q. And then we would be adding 6 there. And so the 6 would come from the 2r, which would be 2 times 3 is 6, is 35. And we know 35 is divisible by 7 because 7 times 5 is 35. And so because of this, we know that 2,951 is also divisible by 7. Moving on to question 2. This question was about the process of nines, I believe. Yes. It was about the process of nines, and it gave us 4 different examples to go by. And so to use the process of nines, for one, is to find the remainder of each of the numbers when they're divided by 9. So for example, the number 416 that we see, when we divide it by 9, it equals 46.2. And so the 2 is what we're going to be working with when we are using the process of nines. And so that's going to be the same for each of these numbers. So 7,490 divided by 9, we're going to use the 2 that comes after the decimal. And the same thing for 69,844. It equals, divided by 9 equals 7,760.4, and we're going to use that 4 after the decimal. And so what we do is we add up the decimals, or the remainders that we were given, 2 plus 2 plus 4, and we know that equals 8. And we can see if that is divisible by 9, or we can just divide it by 9 rather. And if that decimal that we get there is the same as what we get when we divide the sum that's given by 9, then we know that the problem that it gave us is correct. It checks out. And so since we can see that 112,790 divided by 9 equals 12,532.2, and 8 divided by 9 on the right equals 0.8, we know that it does not check, and that 416 plus 7,490 plus 69,844 does not actually equal 112,790. And this is the same method that we use throughout the rest of the problems. It's the same for addition and subtraction and multiplication. And so we'll look at the part D. This is 337 times 620. And so we're going to take these numbers and divide them by 9, just like we have been. And we get 37.4 and 68.8. So we're going to use the 4 and the 8, like we know to do. And we're going to multiply those together and get the number 32. And when we divide that by 9, we get 3.5. And so when we multiply, or when we look at the answer that we're given for the multiplication problem, 209,940 divided by 9, it gets 23,326, I believe, 0.6. And so the 0.5 and the 0.6 are not the same, so that does not check. And we know that if we do actually multiply 337 by 620, we actually get 208,940. So it's about 100,000 or 1,000 off in the answer that's given. And so moving on to part 3, or number 3, this question was about the colored rods. And I found this to be interesting and useful because I am a visual learner, so I like having colorful things to look at when I'm trying to learn and do problems. And so this one I found to be pretty simple, pretty straightforward. The first question is to show which rods will measure the 9 rods. And this is a good question for like divisibility, because we know that if we can put smaller rods together and see that they add up to be the larger rod, then we know that that number of the larger rod is divisible by the size of the smaller rod. So for example, we have the 9 rod, and I have it drawn out, and we know, for example, that 3 times 3 is 9. So if we get 3 of the little 3-inch or centimeter, whatever size they are, rods, then they will add up to that 9 rod that we are trying to find. And so it works the same with the 1 rods. If we add up 9 1 rods, then we will get an equal length of the 9 rod. And so this is the same concept in parts B and C and D. And then we're asked to give all the numbers that can form an 18 chain, which is a 10 rod and an 8 rod put together. And so I found that one 18 rod, or one 18 train, which is the 10 and the 8 put together, and then 18 1 rods could also make it, 2 9 rods or 9 2 rods, 3 6 rods or 6 3 rods could make the 18 train. And so I found that these colored rods would be useful for many things in the classroom, but most of all, it would be really helpful for finding the greatest common divisor, like I just said earlier, to see how many of the smaller blocks will fit together to make the one longer train that you're trying to find. And so moving on to number 4, I found this to be a little bit intimidating at first, but I found that it's not as difficult as it first may seem. The LCM method is a visual method. It's for finding the least common multiple of a set of numbers, and you want to find these in prime power form. So prime power form means that you want the final numbers that you come out with to all be prime numbers, and this means that they can only be divided by the number 1 and the number itself. So we can see in this first example, we're given the numbers 48, 25, and 65. And so the numbers 25 and 65 are easy because we know they can be divided by 5. 48 cannot be, so we'll deal with that later. But we can first divide it by 5, and 25 divided by 5 is 5, and 65 divided by 5 is 13. So 5 and 13 are already prime numbers, so we're already almost done with the problem. We just have to get 48 down to just 2 prime numbers. And so we can do that by first dividing by 2, as you can see, and get 24. Divide by 2 again and get 12, and then divide by 3 and get 4, and then 4 can be divided by 2 and 2. And so we see the numbers down the left side and on the bottom row are 5, 2, 2, 3, 2, 2, 5, and 13. And so we can write these in one simple equation with superscripts to show how many of each number there is. And so we have 13 times 5 squared times 3 times 4 times 2 to the 4th power, rather. And so this is really a simple way to find the least common multiples of a set of numbers. And so it was the same for even the bigger numbers. And I like this method because you can adapt it to how big of a problem you're trying to work. You can do just 2 or 3 small numbers, or you can even go up to 6 or 7 bigger numbers, and you can still find the least common multiples and the prime powers of all of these numbers using this method. And then number 5, this question was about the gears, and the smaller gear and the bigger gear. And so to find the answer for this, the question is, how many more revolutions will the small gear have to make before A and B are in the same position again? And so to find this, I may have done it the hard way, but I just started finding multiples of each of these numbers. So I started with 84, and I did 84 times 1, 84 times 2, 84 times 3, and so on, and found 5 numbers, and then I moved on to the number 48. And I looked at these numbers that I first found, and I found the first number that they both had in common, which was 336. And so since the number 84 gets to 336 in 4 revolutions, and the number 48 gets to 336 in 7 revolutions, this means that the smaller gear has to make 7 more revolutions before, or not 7, 3 more revolutions before it is at the same point as point B. And so last but not least, number 6. I like this problem. I find it kind of fun. It's kind of like a Sudoku puzzle. And this is just a magic square. And in order to solve a magic square, first you have to find the magic number. And the magic number is found by adding up the given numbers and dividing that number, the sum that you find, by the number of boxes in a row or in a column. And since this box is just a 3 by 3, just 3 across, 3 down, we know that like -7 plus -6 plus -5 plus -4 plus -3 plus -2 plus -1 plus 0 plus 1 equals -27. And when we divide -27 by 3, the 3 boxes, we get -9. So the magic number in this problem is -9. And this simply means that each box, when added up with the next one, like the 3 across the top, need to add up to be the number -9. And all of the rows and all of the columns, each diagonal, all need to add up to the number -9. And so it's kind of just a game at this point, finding which numbers will go in which box to get this magic number. You can't repeat any numbers. Each number can only be used once. And it helps you out by giving you a couple of given numbers, so you can kind of work around those. And I found that 0 plus -5 plus -4 equals -9. And -7 plus -3 plus 1 equals -9. And -2 plus -1 plus -6 equals -9, and so on. So I found that to be kind of fun and interesting. It's probably, if I had a favorite, it would probably be my favorite problem of the homework. But that is all for this session, so I hope you enjoyed. Thank you.